Join the happiness. Admissions open. SRM Ishrae Engineering College.
Chetan sir. Sir, please mute it, sir. Chetan sir. Chetan sir.
Sorry, sir. Okay.
Okay. So, good evening to everyone. I welcome you all for the 2 weeks online workshop on energy simulation and CFD analysis in buildings. Today we are on day 3. We are going to discuss about the summer and winter air conditioning. There is a small change in the topic because today we are going to start with the psychrometry, and then we are going to discuss about summer and winter air conditioning. Because tomorrow fully I want to dedicate for air conditioning load estimation. Okay, so for that I have done a small alteration. Please pardon me. Okay, so I will go for the presentation. So today we are going to discuss about the psychrometry as well as summer and winter air conditioning. Okay, so what is the psychrometry? Okay, so we are going to study about the air and the air conditioning. Okay, so for that first we need to know about what is the dry air. Okay, so the dry air is the one which is not containing any water vapor. Okay, so that is called dry air. Okay, so, but atmospheric air. Okay, so atmospheric air will always contain some amount of water. Okay, or moisture. We can call it as moisture. Okay, so dry air means no water vapor at all. Atmospheric air, it will be containing some amount of water. Okay, so the water vapor, okay, so it plays an important role. That small amount of water vapor which is present in the atmospheric air, it plays an important role in the air conditioning. Okay, so that is what we have to understand. Okay, so how we today we are going to discuss about air properties of air and psychrometry and air conditioning. Okay, so first, how we will be calculating the enthalpy of dry air. Okay, so the enthalpy of dry air, so we will be calculating by, okay, so we will be calculating by Cp into T. Okay, and if you want to find a change in the enthalpy, so we will be finding out Cp into delta T. Okay, so that is how we will be finding. Okay, this is for dry air. Okay, if I am having similarly water, if you the main components of the atmosphere, it is dry air plus water vapor. Okay, so the dry air, okay, so dry air plus water vapor. So I can say that the partial pressure of dry air plus partial pressure of water vapor, it is equal to the total pressure of the air. Okay, and water vapor in the air behaves as if it is existing alone, and it will follow the gas relation PV is equal to RT. So we may be wondering, but it behaves like that. It is existing in a superheated state, so it obeys the ideal gas relation PV is equal to RT. Okay, so and about water vapor which is present inside, how we calculate the enthalpy. So the water vapor which is present in the atmospheric air, so we calculate the enthalpy, okay, as H of T. Okay, so H of T, it will be latent heat plus the specific heat into the superheat temperature. Okay, so the latent heat we take it from 0 degrees centigrade. This is phase change from liquid to vapor or vapor to liquid. Okay, so that phase change value we are taking, and since the water vapor, it has low pressure and high temperature, so we can assume that water vapor is an ideal gas. Okay, at high temperature we will be seeing that the enthalpy lines and the temperature lines, both it will be coinciding. Okay, so that is what we will be seeing. So that is how we can take water vapor as ideal gas, and we can use the ideal gas relation. Okay, so the first and foremost, okay, so what are the temperatures? Okay, so we have two temperatures. So one is wet bulb temperature, other one is the dry bulb temperature. So what is a dry bulb temperature? So dry bulb temperature, it is the temperature which we are measuring using our thermometer. If you are measuring the temperature of the air using our ordinary thermometer, so it is called as the dry bulb temperature. Okay, so then what is wet bulb temperature? So wet bulb temperature, first we need to know why they started using wet bulb temperature. Okay, wet bulb temperature, it was used in olden days, because in olden days we didn't have any electronic instruments like what we are having today for measuring the humidity. Okay, humidity or RH. So they have followed an indirect method of measuring the wet bulb temperature. Okay, so the wet bulb temperature indirectly gives the amount of moisture present in the air. So the amount of moisture present in the air, how we are finding it out? So we are taking the thermometer, we are putting a wick, and we are dipping it in the water, which is in equilibrium with the surrounding. So for that, what we are doing, we are having the wick, we are dipping it in water, and we are making the air to flow through that. In that process, the water will come to equilibrium with the surrounding. Okay, so if you measure the temperature like the arrangement what is shown here, then the temperature, it is called as the wet bulb temperature. Okay, So the instrument which is used for measuring that, it is called as wet bulb thermometer. Okay. Similarly, the instrument which is used for measuring the dry bulb, so it is called as dry bulb thermometer. Okay. And what is the significance of wet bulb temperature? Okay. So always we know the dry bulb temperature will be greater, wet bulb temperature will be lower. It is very simple to understand. So because almost the wet bulb temperature, it will be giving the water temperature, water if it is at the equilibrium, okay, with the surrounding. So that means the water temperature, usually it will be less than the air temperature. So in that case, what will happen? The difference, okay, so the difference between the dry bulb temperature and the wet bulb temperature, it is called as wet bulb depression. So this wet bulb depression, it indirectly tells us whether the air is dry or not. Okay, so or if the air is dry or humid. Okay, if the wet bulb depression, if it is higher, okay, so then the air will be dry. Okay, similarly, if the wet bulb depression is very much lower, okay, or equal to 0, so then we say the air is humid. Okay, so air is humid. So we know at saturation, the wet bulb temperature and dry bulb temperature will be equal. In other words, the wet bulb depression, it will be equal to 0. Okay, wet bulb depression, it will be equal to 0. So that we can check it using a psychrometric chart. Okay. So the wet bulb temperature, it represents the adiabatic saturation temperature. So if you are saturating the, okay, so if you are saturating the air with water, okay, so whatever the temperature we are getting, so it is called adiabatic saturation temperature. So our wet bulb temperature will be closer to that adiabatic saturation temperature. Okay, so that will help us to find out what will be the humidity in the air. Okay, but nowadays we are able to measure the specific humidity and the RH directly using different sensors. Okay, so and now we are not using. In olden days, what they did is they used to measure using the sling psychrometer. They used to measure the dry bulb temperature and wet bulb temperature. Then they will go to the psychrometric chart to find out what is the specific humidity and the relative humidity. So it was very important in olden days. But now we are measuring these the moisture content in the air directly, okay, using latest sensors. So then the next important parameter is the specific humidity. So what is specific humidity? Okay, so the specific humidity, it tells about amount of moisture present in the air. Okay, amount of moisture present in the air. So it is the ratio of mass of water vapor to mass of air. Okay, so a lot of these things are there. Okay, you can M is equal to PV by RT, and V and T will be same, and we can substitute RV, that is gas constant for vapor, gas constant for air, and after that you will be getting this expression. So we are not going to discuss in detail about the formula. So we are going to discuss about what is the significance. Okay, what is the significance of specific humidity? Okay, the specific humidity, it represents, okay, so the specific humidity, it represents the amount of moisture which is added to the air. Okay, so it is the ratio of moisture to dry air. So mass of water vapor to mass of dry air. So if dry air amount is constant, so if I am adding moisture, what will happen? So gradually the specific humidity will be increasing. So now you are seeing the psychrometric chart. So the vertical axis in the psychrometric chart. Okay, so it will represent the specific humidity. So here you can see this is specific humidity. Okay, so when I keep on adding the moisture, what happens? The amount of moisture will be increasing. In other words, the specific humidity will be increasing. If the amount of dry air is same, if I am adding the moisture or water vapor, so what will happen? So the specific humidity will be increasing. Okay, and most of you will be knowing that the moisture present in the air, it is associated with the latent heat. So that means if you want to if you want to add moisture or the remove moisture, okay, so the latent heat will be involved. Okay, so accordingly this axis, so it is latent heat axis. Okay, so this axis where we take the moisture content, it is the latent heat axis. Okay, and this axis whatever we are having, so this is the dry bulb temperature. Okay, so this is the dry bulb temperature. So this is called as the sensible heat axis. Okay, so this is sensible heat axis, and this axis, it is latent heat axis. So that is what we have to understand. Okay, now we know what is the specific specific humidity or absolute humidity. It is the ratio of mass of water vapor to mass of air. So if I keep on adding the moisture in the air, okay, so the amount of moisture, the specific humidity will be increasing, okay. And at a particular temperature, if I keep on adding the moisture to air, so it is not possible for me to add moisture infinitely, okay. So there is something which will be stopping, okay, with the amount of moisture addition, okay, for a particular temperature. So that parameter, it is called as relative humidity, okay. When I'm adding when adding sufficient amount of moisture to the air, so I say the air is getting saturated. That means if I keep on adding moisture to the air, at some point air will get saturated. Okay. So for a particular temperature, so there is a limit for which you can add moisture, okay, to the air, okay. So that is decided by relative humidity. So what is relative humidity? So the relative humidity, it is the mass of water vapor present in a given volume of air to the mass of water vapor which is present at saturation in the same volume, okay, at the same temperature, okay. So that means in simple words, if you want to tell, so you can tell that it is the ratio that the moisture can hold, okay. It is the ratio of moisture that the air is holding now compared with the maximum amount of moisture that the air can hold, okay, at the same temperature. So that is called as relative humidity, okay. So relative humidity, it is an important parameter, because if relative humidity is less, it means that you can add more amount of moisture. For example, if I'm having 10% relative humidity, there is a 90% potential of adding the moisture, okay. So that is how you have to understand. Similarly, if I'm saying, if I'm having 90% relative humidity, so that means there is only less, that is 10% moisture addition only, it is possible. It is almost near to the saturation. So it is difficult to add moisture. So that is what you have to. So this parameter, it is decided by the relative humidity. So we will find that the relative humidity will be increasing with the temperature. So that means when the temperature increases, the relative humidity also increases. That means the capacity to hold the moisture, that also increases. Because, you know, when I increase the temperature, the molecules will be moving at higher velocity. So that means it will not condense immediately. It will not condense and removed out immediately, okay. So the potential for adding the moisture will be more at a higher temperature, but at a lower temperature, the molecules will be moving at lower velocity. It will always try to separate out, okay. So because of that, okay, so at high temperature, this point you just put it in mind, because we are going to discuss this in winter air conditioning also, okay. When I increase the temperature, I can add more moisture to the air, okay. Similarly, if at a lower temperature, I can add only less moisture to the air. So this is important concept we should know, okay. So that how you can calculate, okay. So this is how the relative humidity is linked with the specific humidity. I'm not going to the formulas because all of you might have studied. So just I will mention about the physical significance only, okay. So if I'm taking the air, okay, so the total enthalpy of the air, atmospheric air, so I will be having a enthalpy of dry air plus enthalpy of the vapor. So the enthalpy of air, it is the mass of air into enthalpy of air plus mass of vapor plus enthalpy of vapor, okay. So now I can divide throughout by mass of air. So I have MHA plus MV by MA. So already we know MV by MA, mass of water vapor to mass of air, it is specific humidity. So that is how the enthalpy is calculated. So the total enthalpy of moist air, it is the dry air enthalpy plus the specific humidity into the enthalpy of air, water vapor. I'm sorry, enthalpy of water vapor. Okay. So specific humidity into the enthalpy, that will be giving me the total enthalpy for the moist air. Okay. So now at any point, okay, so at any point, so the enthalpy is given by H of air plus specific humidity into. So if I have specific humidity directly, I can add, okay, the air enthalpy with the water enthalpy. Otherwise, I cannot add it. Okay. Okay. So we will go to the next important parameter or property. It is called as dew point temperature. So what is the dew point temperature? Okay. So dew point temperature, it is the temperature at which the condensation will be taking place. Okay, condensation will be taking place, and moisture will try to separate out from the air. Okay, so that point, it is called as the dew point temperature. We know that we can draw the TS diagram for water. So that is called as properties of steam. And most of us, when we are studying in the power plant and other topics, so our temperature range will be very much higher. But when we are studying in the air conditioning, okay, so the temperature will be lesser. That means our evaporation and condensation will be taking place at room temperature. So that means the corresponding pressure, if you try to find out, it will be very much lesser. Okay, it will be in terms of kilopascals only. Okay, so that means our phase changes. Okay, so that means condensation and evaporation, it will be taking place at room temperature, less than room temperature. Okay, cooling coil temperature. So that means the corresponding vapor pressure will be very much lower. So now I am taking one such curve which is having a lower vapor pressure. So just we are taking for water vapor alone. Okay, so air we are not taking. Air will be in the superheated state. Okay, so water only, it will be changing its phase. Okay, so I am taking one such water vapor curve. So you know, when I am going from this side to this side, so that is we are adding heat. When I am coming from this side to this side, I am removing heat. Okay. Similarly, when I am going from this side to this side, the liquid water will be converted into vapor. Similarly, when I am coming from this side to this side, vapor will be converted into liquid. So the temperature where the phase change is occurring, so we usually will be calling it as the saturation temperature. So here we are calling it as the dew point temperature. Okay. So that means the dew point temperature, it depends on the partial pressure of water vapor. So that is very, very important. So you know, in the atmosphere, the partial pressure of water vapor, it can increase or decrease. Okay. For example, you take a Chennai condition. Okay, so it is a humid condition. So the partial pressure of water vapor at Chennai, it will be higher. So if you take Delhi or Bangalore, okay, so there the partial there the humidity will be less. So there the partial pressure will be less. So in other words, the saturation temperature, okay, saturation temperature in Chennai, it will be very much higher. Saturation temperature at Bangalore and Delhi, it will be lower. In other words, the dew point temperature at Chennai, it will be very much higher. And the dew point temperature at Bangalore and Delhi, it will be very much lower. So what is the significance of that? So it means that at Chennai, we have a high dew point temperature. A small reduction below the dew point temperature, immediately water will be condensed. So that means, so you think if you are driving a car, or if I am putting a soda can like this in the table, so the tendency to condense it will be more in the Chennai, because my dew point temperature, it will be higher, but this temperature compared to that, it will be very much lower. So because of that, there will be lot of condensation over the soda can. And if I am going to Bangalore, Hyderabad and Delhi, so interior place, the humidity will be lesser. So that means the partial pressure of water vapor will be lesser. So that means the dew point temperature will be lesser. So if the dew point temperature is lesser, even if there is a small drop in temperature, there will not be condensation. So in those places, if you want condensation, so that means you have to bring down the temperature at a very low level. Okay, so then only condensation will be taking place. So in Chennai and other coastal areas, a small drop in the temperature, immediately condensation will be taking place. Even in car AC, in air conditioners and all, condensation will be taking place. But if you go to these places, interior dry places, there at very low temperature only condensation will be taking place. So now what is the moral of the story? Dew point temperature, it is related to the partial pressure of water vapor present in the atmosphere. So then dew point temperature, it is also dependent on the specific humidity, because specific humidity, it is what? It is related. If specific humidity is more, the partial pressure will be more. Partial pressure of water vapor will be more. Similarly, if the specific humidity is less, the partial pressure of water vapor will be less. So that is the importance of a dew point temperature. Dew point temperature is very important because the condensation, okay, so the condensation, it is decided, condensation in the coil and the other surfaces, it is decided by the dew point temperature only. Okay, so now we have seen a few parameters. So now that we are seeing what are all the other parameters which we have to discuss. Okay, so we have taken the horizontal axis. So this is the dry bulb temperature. When I am moving in this direction, I am adding heat. Okay. Similarly, if I am moving in the opposite direction, I am removing heat. So this process, this is sensible heating. If I am moving horizontally like this. Similarly, if I am moving in the opposite direction, so this is a sensible cooling. Okay. So that means this is a sensible area. Okay. So horizontal axis, it is a sensible area. Okay. That is why we are having temperature. The vertical axis, when I am adding moisture, the specific humidity increases. So when I am removing moisture, the specific humidity decreases. Okay. So it is associated with the moisture. So that is latent heat. Okay. It is associated with the latent heat. And one more thing, what we have to note is when I am increasing the specific humidity, I am finding that the water vapor pressure also it is increasing. Okay. Similarly, if I am decreasing the specific heat, the water vapor pressure also it will be decreasing, which is obvious because we discussed now. Similarly, one more thing also we have to note, that is when I am increasing the specific humidity, we are finding that the dew point temperature also will be increasing. For example, if I take a location here, okay, for this is the specific humidity. For that, the corresponding dew point temperature will be here only. Okay. Similarly, the pressure will be here only. Similarly, if I take this point, okay, so if I'm taking this point, the specific humidity will be this value. So the corresponding dew point temperature, it is increasing. So that is what I told. Okay. So when I am increasing the specific humidity or vapor pressure, the dew point temperature will be increasing. When the dew point temperature increasing, there is more tendency for condensation and separating out. So you may be knowing, suppose if I am here, if I am moving here I have more tendency for condensation and separating, okay, compared to this place. Okay, so where I have to move up to this for the separating condensation and separation. Okay, so this point we have to note it. Okay, next, so this is the saturation line. Okay, so this is the saturation line or 100% saturation line. Okay, so the lines of relative humidity. Okay, so these lines will be running like this. Okay, so maybe I will be showing it. I will show it here. So here you can see this is a 100% saturation line. So this is 90% saturation, 90% RH line, 80% RH line, 70% RH line, 60%. So like that it will come. Okay, so we have it up to 10%. Okay, so all these lines which are moving here. Okay, so those are all RH lines. Okay, and this line is the 100% saturation line. Okay, 100% saturation line. So that is what we have to understand. So the next thing is when you compare the dry bulb temperature, wet bulb temperature, and the dew point temperature. Okay, so what is the dry bulb temperature? It is the temperature at any location which you are measuring using the thermometer. So what is the wet bulb temperature? So I told wet bulb temperature, it is related to the equilibrium temperature of water. So if the equilibrium temperature of water, so it will be always lower than the atmospheric temperature. Okay, except at 100% saturation. In other places, always the wet bulb temperature will be less than the dry bulb temperature of air. Okay, so for this you can know. Suppose you think this is now we are having winter. So when we are going for sleep and when we are getting up in the early morning, so you go and touch the water. So you will know that water will be very chilly. So what is the meaning of that? So that means night times we are having dry. Okay, we are having dry climate. So because of that, what is happening? The water temperature is going down. While the dry bulb temperature, it will be higher. The water temperature will be much lower than that. So that is why if I put my hand in the water, so I feel it is very cold. So that means whenever you are feeling that water is very cold compared to your ambient temperature, so that means the atmosphere is dry. So that is what we have to understand. Okay. Similarly, if you put your hand in same water around the afternoon, so what happens? That the difference in temperature is not that much. Okay, it is not that much appreciable. So what is the meaning of that? So it means that during the daytime, okay, so the wet bulb temperature is closer to the dry bulb temperature because the humidity will be higher. So you may be knowing during winter season, night time, it will be the temperature drops, all the moisture will be getting condensed and it will be separated out. So the night time it will be dry. Okay. So because of that, the difference between the wet bulb and the dry bulb, it will be very much higher. Okay. And so the wet bulb depression will be higher. So we can take it like this. During daytime, the wet bulb depression will be smaller. So that is how we can understand the wet bulb depression. It represents the degree of dryness in the atmosphere. Okay. And the dew point temperature will be much less than that. Okay, dew point temperature, it is the temperature at which uh, the moisture in the air will condense and separate it out. Okay, so that will be much lesser than that. Okay, but how the dry bulb temperature and wet bulb temperature, how you have to remember? So it's very simple. If you take water and spray it in air, okay, if you are spraying water in the air, okay, so if the water temperature, if the air temperature is going down, so if it is going down, it means that the air is the surrounding is dry. Okay, so that means it is accepting the moisture and it is reducing its temperature, air temperature. Okay, so it means that the air is dry. Suppose if you are taking water and spraying in the you are spraying it in the air. So if the surrounding temperature is not dropping, see, especially like in places like Chennai, Cochin, and coastal climates, Visakhapatnam, so there it will not be dropping. Okay, so you spray the air in water, the air temperature will not be dropping. So this is because the higher humidity, the wet bulb depression will be lesser. Okay, so that means in interior places, if I spray the water, okay, if I spray the water in the air, so I will find in Bangalore or Hyderabad or Delhi, if I spray the water, okay, so we will find that there will be a drop in temperature of the air. Okay, so that is why air washer or air coolers, we use it in the interior place. We don't use it in the coastal area because it will not have its effect. Okay, so that is very important. Okay, so the wet bulb temperature, okay, and the wet bulb temperature, it is related to the enthalpy also. Okay, because the wet bulb temperature, for particular wet bulb temperature, you will be having a particular enthalpy only. So that enthalpy, it is the enthalpy of saturation. Okay, so you can see. Okay, so you can see. So here these are all the enthalpy lines. Okay, so these are, so according I have the wet bulb temperature lines running like here. Okay, so I have the wet bulb temperature lines running here. Okay, for each enthalpy line, I will be having one wet bulb temperature line only. Okay, and why it is wet bulb temperature is constant throughout this line? It is because of adiabatic saturation process. We are not allowing heat to enter or enter into the system. So that means we are isolating the system. So that means the enthalpy will be remain constant. Okay, so the enthalpy will remain constant along this wet bulb temperature line or adiabatic saturation line. Okay, so that also we have to understand. Okay, and yeah, so the next thing what you have to understand is the when I increase the RH. Okay, when I increase the RH, so you will find that or in other words, if I am increasing the dry bulb temperature, the RH will be increasing. Okay, increasing. So that I can find out. Okay, so when that I can find it out when I'm using a okay, in sensible cooling process. Okay, so a sensible cooling or heating process. Okay, so I will find that when I'm increasing the temperature, so the RH also will be increasing. Okay, so here you can see from here it is having some RH. When I'm moving from here to and I'm heating, the RH is decreased. So when RH is decreased, what is the meaning of that? So the meaning of that is, so suppose you think from here, if I'm drawing a horizontal line, okay, so the starting point, it will be 80%. So when I reach this point, okay, so it is 30%. So what is happening here? I can add only this much amount of moisture because saturation is here. When I come to 30%, you see from here the saturation line is somewhere there. So that means there is a tremendous potential of adding moisture. Okay, so that is what we have to understand. Okay, so that means when I increase the dry bulb temperature, the RH also increases. In other words, the capacity to hold moisture, it will be increasing. If I draw a small line, then you can understand. Okay, so just 1 minute. So I hope you are able to see this now. Okay, so now we will draw a horizontal line. Okay, so think that I'm drawing a horizontal line like this. So this is the starting point and this is the ending point. Okay, so now from here, this is the potential. Okay, so this is the potential for adding the moisture. So that means I am at 90%. The saturation is here. The potential for adding moisture is this much only. So correspondingly, if I take the humidity difference, okay, so I'm sorry. Okay, so correspondingly, if I take the humidity difference, okay, so correspondingly, if I take the humidity difference, so this will be this much only. Okay, so this will be this much only. Now at the final condition, okay, so that is at this point, okay, how much humidity I can add, okay, so this much, okay, so this much amount of humidity. So the potential, how much amount of moisture I can add from this point to this point, okay, so this much amount of moisture I can add. So that is what I say. If I go for sensible heating, okay, the how much moisture I can add. So at this point you can see this difference in moisture is smaller only. This much only you can add it. But when I come to this point 2, so the difference is moisture is very much higher. So this much amount of moisture I can add it. Just multiply. Find the difference in specific humidity, multiply by the amount of air. You will find that the quantity of moisture which you can add will be very much higher. So this is very much useful in a process like drying and all. It will this concept will be very much useful. So usually they will be heating the air. Then after that they will be sending it for drying. So it will remove a lot of moisture. Okay, so that is the concept. Okay, and now we will go back to our discussion. Okay, so now we will go back to our discussion, and okay, so. Okay, so now we have so this is the sensible axis. This is the lantern axis. So we have the sensible heat factor here. We will study about that. So these are all the RH lines that we have studied. Okay, so these are the enthalpy lines. Okay, so the enthalpy lines. Okay, so the enthalpy will be increasing from here to here. Okay, the enthalpy will be increasing, and these are all constant enthalpy lines. Okay, so that we have to know, and we have the specific volume lines. Okay, so the specific volume will be higher at this point at this places, and the specific volume will be lesser at these places. Okay, so that means what? Density will be higher because these are colder places. The density will be higher, and these are warmer places. Okay, so that means the density will be lesser. Okay, so that is what you have to understand. Okay, we will proceed with our discussion. Okay, these are the things what I have told just now, and one point we have to know. So that is at saturation. At saturation, we are finding that the dry bulb temperature, wet bulb temperature, and the dew point temperature, it is matching. So it is it is known because dew point temperature is again saturation temperature, and wet bulb temperature. Okay, if it is reaching the dew point temperature and the dry bulb temperature, already I told, if wet bulb depression is 0, it is saturation. So what is the meaning of that? Dry bulb temperature minus wet bulb temperature is 0. 15 minus 15, it is 0. So that means at saturation, I will have all this dry bulb, wet bulb, and dew point temperature will be same. Okay. Now we will go to the air conditioning process. Okay. So most of you, I think, you may be familiar with the air conditioning processes. So we will go by process. Okay. So I told this is the horizontal axis. This is sensible heat axis, sensible heat axis. And this is the latent heat axis. Okay, this is because of moisture addition and moisture removal. This is because of sensible heat addition and sensible heat removal. Okay, now from this point, okay, when I'm moving horizontally, so this is called sensible heating. Okay, so this is sensible heating. Similarly, if I'm moving in the opposite direction, this is sensible cooling. It is known to you. Okay, because this is a dry bulb temperature, it is increasing. When I'm moving in this direction, dry bulb temperature increases. Similarly, if I'm moving in the opposite direction, the dry bulb temperature decreases. Similarly, if I'm adding moisture, it is the air is getting humidified. When I am moving in the opposite direction, that means I am removing the moisture. So that means dehumidification of air is taking place. Okay, and what is this process? So it is combination of these two. Like very simple, heating and the humidification. Okay, so it is a combination of this heating and humidification. Okay, similarly, if I have a line like this, so that will be cooling and dehumidification. So the line can go like this also, that is cooling and humidification. Similarly, the line can come in this direction also. So that is heating and dehumidification. So all these processes are possible. Okay. And in the air conditioning process, it will be following the thermodynamic laws. Okay. So there will be mass balance. Mass entering will be equal to mass leaving. And this, separately, the mass will be balanced for air as well as for water. So in a process, the air entering, okay, the sum of air entering, okay, will be equal to the sum of the mass of the air leaving. Similarly, if there is no condensation or no moisture addition, So moisture balance also will be there. Okay, so the sum of the moisture at inlet will be equal to sum of the moisture at the outlet. How I can write in terms of air? You know that mass of air into specific humidity. Okay, the same thing I'm writing it in this form. Okay, so then energy balance it will be there. Mass balance will be there. Then energy balance will be there. Okay, thermal energy balance will be there. So for that, it will satisfy steady flow energy equation. So I have the energy at inlet will be equal to energy at outlet. So this can be applied for all the air conditioning processes. So the Q in, it is the heat supplied at inlet. So you think that this is at inlet condition, okay, air inlet condition. This is air outlet condition. And similarly, W in at work input at inlet, and the summation of all the enthalpies or the energies, okay, at inlet will be equal to Q out, W out, and this all the enthalpies at outlet. Okay, so these things, if you are a mechanical engineer, you will be very familiar. Okay, so you should be knowing energy balance will be there. Okay, okay. So next we are going to the sensible heating process. Okay, so what is sensible heating process? So now I think we should be familiar with what are all the various accesses in the cyclometric chart, and what are the various processes in cyclometric chart. This way heating, this way cooling, this way adding moisture, removing moisture. Okay, so now we are ready for knowing about various air conditioning processes. So first famous process, okay, in the air conditioning is simple heating or simple cooling, or in other words, technically it should be sensible heating with a specific humidity constant. Okay, so now sensible heating with this specific humidity constant, that means what? Air is entering, okay, and there is a heater, okay, electric heater inside that. So what is happening when the heating process is taking place? You will find that the specific humidity will be constant because you are not adding any moisture externally. So because of that, the specific humidity will be constant. So in the process diagram, okay, in the psychrometric process, this will be like this. So from 1 to 2, okay, sensible heating is taking place. Okay, so sensible heating will be taking place. So what is that you are finding? The specific humidity is constant. That is the main condition for sensible heating. Okay, and but RH is increasing. You can note that because RH can increase because it is the capacity to hold the moisture, so that it can increase. But the moisture is not increasing. Okay, the state of moisture can change because of heating and cooling. The state of moisture can change, but the amount of moisture or the mass of moisture it cannot change. So that is how specific humidity is constant. Relative humidity is increasing. That is for sensible heating. When I am going for sensible cooling, so I will be going from hot state to cold state. So that means here I will be having the cooling coil. So from here I will be moving in the opposite direction. So from higher dry bulb temperature, I will be moving towards a lower dry bulb temperature. Okay, so that is called as a sensible cooling. Okay, and again I can go for a mass balance. So here mass of air at inlet is equal to mass of air at outlet. Specific humidity at inlet is equal to specific humidity outlet because that is the condition. Specific humidity is constant. And the energy balance, what is the energy balance? So if air is coming to the heating coil, before the heating coil, the air will be at a lower enthalpy or lower temperature. So when air is moving to the heating coil, it will pick up the enthalpy or heat, and its enthalpy will be rising, or in other words, temperature will be rising. So that is what is happening here. Okay, so that means this enthalpy will be greater and this enthalpy will be lesser. So greater enthalpy minus lesser enthalpy into mass flow rate of air, that will give you a Q. Or if you want by energy balance, MA into H1 plus the heating. Okay, so this will be equal to MA into H2. So that is it. Okay, lesser enthalpy MA into H1 plus this heating, it is equal to greater enthalpy, that is MA into H2. So this is the energy balance. Okay. So like that you can work out. Similarly for cooling also we can work out. So you can do it. So that is the thing. Okay, so that is the thing. Okay, and a sensible heating, it will be taking place. Okay, whenever you are having an electric heater. Okay, whenever you are having an electric heater, so sensible heating will be taking. Washer, air washer. There should not be any air washer. There should not be cooling below the dew point temperature, because if you are cooling below the dew point temperature, what will happen? Moisture will separate that out. Okay, so then the humidity will be dropping. So that we have to see. Okay, next. So now we are going to the air washer system. So these are the smaller systems. So if you know about the air washer system, so you can be familiar with any type of psychrometric process. Okay, so if I take a air washer system, so I will find. Okay, so I will find that there are various conditions. Okay, so there are various conditions which it has to satisfy. So first we will try to know this condition. Okay, so 1 minute. So we will go to the air washer system. So I request everyone. So there may be a small delay. Okay, so please pardon with me because we have to cover a few portions. Okay, just pardon with me. Okay, so I will be taking an air washer system. What is an air washer system? So air washer system, just it's very simple. If air is entering, we are spraying water over that. Okay. So while spraying the water, so we require we will require a tank. We require a level control system. So then we require a pump, and you have to either heat the water or cool the water for obtaining various conditions. So like given in this system, so we have to either heat it or cool it. Okay. So let us see where and all we have to heat it and where and all you have to cool it. Okay. So first, okay. So first we will see the first system. Okay. So the first system is this one. Okay. So this is the starting point. Okay. So this is the starting point for the air washer system. So air is starting from here. Okay. And here you can see when air is moving from 1 to 2A, okay, 1 to 2A, so the temperature of water, okay, it is greater than the temperature of dry bulb temperature. So this is this is a dry bulb temperature. So in other words, if I am heating the water above the dry bulb temperature and if I am spraying it in the air, what will happen? The air will be getting heated and humidified. So this thing, okay, so this is heating and humidification. This is heating and humidification. So for that, what is the condition? If the the surface temperature of the water, if it is whatever water we are taking here, okay, so if the surface temperature of the water, if it is greater than the dry bulb temperature, so we will find that heating and humidification will be taking place. Next, what is happening? The second process is now we will take the same water and we will send it at the dry bulb temperature itself, okay, for spraying. Okay, so here for spraying, we will take the same water and we will send it at dry bulb temperature. So you may ask how? Somehow, okay, somehow you should have a control system that is isothermal, okay, isothermal moisture addition. So because of that, what will happen? Already I told you, humidification will be taking place at a constant temperature. Humidification will be taking place at a constant temperature. So if you compare to this level, so here the specific humidity will be W1, here will be W2B. That means at a constant temperature, we are humidifying. Okay, isothermal humidification. That is what is taking place. So next we will take the next condition. So this is dry bulb temperature and this corresponding. Okay, so this is wet bulb temperature. For this, if I go in this line, this will be the wet bulb temperature. Okay, so this will be the wet bulb. So this will be the wet bulb temperature, because I need this temperatures for reference. Okay, so what I am doing, so from here, now I am spending the water at a temperature less than dry bulb temperature. Now I'm going in this way. I'm sending the water at a temperature less than dry bulb temperature and greater than wet bulb temperature. So what is happening? So this is the process. Okay, so I am sending the water at a temperature less than the dry bulb temperature and greater than the wet bulb temperature. So what is the process here? So this is cooling and humidification. So this is humidification, this is cooling. If I move in this way, cooling. So this is cooling and humidification is taking place. Okay, and so you may be thinking, if your cooling and humidification is taking place, that means what I have to do here? I have to cool it. No, actually you need not cool it. So actually you have to heat it. Okay, so just think from this point. This is enthalpy point. So this is the point. Okay, so 1 minute. So this is the first enthalpy point. So if I want to find the enthalpy for this, I have to go in this axis. So this is the starting point. Okay, and for this, okay, second location, if I want to find the enthalpy, it will be somewhere here. Okay, so now if I'm moving from here to here, what I have to do? Heating only, because enthalpy increasing. So heating only I have to take place. So you are heating the water, but the air is getting cooled. So it is something different. You have to note it. So the next we will go to the next process. Okay, so next process is moving in the at a constant or adiabatic saturation process. Okay, so adiabatic saturation means so totally it is insulated. You are making the spraying the water. Okay, you are spraying the water at a totally insulated condition. Okay, at the wet bulb temperature. Okay, so what is happening again? So again it is cooling and humidification, cooling and humidification. Okay, and next, okay, so next what I am doing, so now I have to note what is this temperature. So you know, horizontally if I am coming from here, so this would be ADP, and this temperature should be ADP temperature. Now if I am spraying the water in the temperature between the wet bulb temperature and the ADP, okay, this is wet bulb temperature and this is ADP. So if I am spraying water in the washer in the temperature between the wet bulb temperature and the ADP, so what is happening? Again here also cooling and humidification only it is taking place. But now you see, if this is the starting point and this is the ending point. Okay, so now if I am moving in this way, so now what is happening? The enthalpy is decreasing. So that means I have to do the cooling. So here I have to do the cooling here. Okay, so here I have to do the cooling. So that's interesting. You can see that is interesting. Okay, so here we are heating for doing the same process, but below the wet bulb temperature we are cooling it. Okay, so for getting it. Okay, and when I am coming, okay, so you know about this process. So this is the process which we have studied now. If the water temperature, okay, so if the water temperature is at the dew point temperature, okay, if the temperature of water sprayed, okay, if it is at the dew point temperature, what is happening is there will not be any change in the specific humidity. So the specific humidity will be constant. So this process is sensible cooling process. Now you have to know that we are doing the spraying, but still we are having sensible cooling process. Okay, so that is we have to know it. So if you are doing it at the dew point temperature, so if you are spraying water at the dew point temperature, so you will find that the specific humidity will be remaining constant. Okay, so this is a sensible cooling process. And the next process is further more interesting. Okay, so I am spraying the water at a temperature. Okay, I am spraying the water at a temperature very much lesser than, okay, so at a temperature very much lesser than the dew point temperature. When I am spraying the water at a temperature very much lesser than dew point temperature, you will find that cooling and dehumidification will be taking place. See, you are spraying water, but still the moisture is removed from the air. How this is happening? So this is the most common. Okay, so most common thing I can explain you very clearly. Okay, so here suppose you think that you are having brine. Okay, so brine will be having a very low temperature. Okay, so even it will be you can have it at -5 degrees centigrade also. So think that you are spraying brine. Okay, if you are spraying brine, so naturally the brine will be, the temperature of the brine will be at less than the dew point temperature of the air. It is possible. So when you are spraying, okay, brine in the air, so what will happen? The moisture present in the air, it will try to condense on the surface of the brine. So that is something interesting to note. So moisture at the surface of the air, moisture in the, present in the air, it will try to condense on the surface of the brine. So because of that, the moisture will be removed from the air. So that means the air will be dehumidified. And also the brine is at low temperature, it is cooled. So that is cooling and dehumidification. So don't always think that cooling and dehumidification it can be done by only cooling coil. You can do it by spraying the water, also spraying the brine also. It is possible. So many interesting things are there. Okay, so this is a very interesting concept. That's why I'm discussing here. And if you understand all these concepts, I think you will understand the cyclometry totally. So that's why I'm discussing this concept. Okay, next. Okay, so from here, okay, so we have seen about the washer. So then now it will be easy for you to know what is the adiabatic saturation process. So adiabatic saturation, that's now we have seen. So if at a constant wet bulb temperature or in total insulation condition at constant wet bulb temperature, if you are spraying, okay, if you are spraying the water, so the process whatever it is happening, it is called adiabatic saturation process. Okay, so if you are seeing it, okay, so the usual constant pressure cooling, okay, due to dew point reduction, so this will go like this. If you are spraying water at adiabatic saturation, so this will go like this. what happens if I move like this? So this is like isothermal, okay, isothermal moisture addition. Just now we have seen, no, at the constant dry bulb temperature, if I am adding moisture, okay, so that is also possible, okay. Okay, fine. So next we are going to the most important thing. So we are here to study about cooling and dehumidification process only, okay, or summer air conditioning process, okay. So the summer air conditioning process, so you know, and we will try to link what we have studied the past 2 days. In past 2 days, we have studied that, that we will be having different seasons in the world, different day lengths in the world, different climatic conditions in the world. Some places may be very hot. Okay, so when there is hot condition, hot and humid condition, we go for cooling and dehumidification. When there is a cold and a dry condition, for example, during winter, if it is in interior USA, okay, or interior Russia, okay, so you will be having a cold and dry condition. So there we have to go for heating and humidification. So the opposite we have to do it. So in hot and humid climatic conditions, we go for cooling and dehumidification. In cold and dry conditions, okay, so we will be going for heating and humidification. So we do the opposite, okay, we do the opposite, okay, so that you may be knowing. So now in air conditioning, so in a summer air conditioning, usually we go for cooling and dehumidification only, okay. So why we are going for cooling and dehumidification? So the outdoor condition, it will be very hot. So for example, if I am taking Chennai, Chennai will be at somewhere here only, okay. So it is very, so this also we have to note it, okay. So this also we have to note it, I think, yeah, so it's not there. So the Chennai condition will be somewhere here only. So it is humid and it is hot also. Hot and humid means this is the zone, okay, very hot and humid, unbearable. So similarly, cold and dry means it is somewhere here, okay. So you can see dry means humidity is very less, and this is cold, so 5 to 10 degrees. So this is maybe in Scandinavian countries, interior Scandinavian countries, interior USA, okay, North America. So you will have conditions like this, okay. So that means where is my condition? So my condition is somewhere here. So from here I have to bring it to here. Similarly, that is called cooling and dehumidification. Okay, so from here, cold and dry place, I have to take it to this place. So that means I have to do the heating and dehumidification. I have to add moisture. I have to add moisture and I have to add heat. Here I have to remove the moisture and I have to remove the moisture and I have to remove the heat. Okay, so I have to remove the heat. So that we have to know it. Okay. So that is what. So this heating and dehumidification systems. This is what we have it in our household air conditioners. For India, we are very familiar with. I'm sorry. In India, we are very familiar to cooling and dehumidification process. Okay. So we will be taking the air outside, hot and humid air, and we will be making it to pass through the cooling coil. So what happens when I am making it to pass through the cooling coil? Okay. So if I go for the cycrometry, so mostly you will be having a tendency to go from here to here. So that is also correct. But the actual process, it will go from this point to this point. Okay, so it will go towards the saturation. From there, after that, it will undergo both moisture reduction will be there and the temperature reduction also will be there. Okay, so please try to understand. So correspondingly, here to here, moisture reduction is there. Similarly, the temperature reduction is there. So that is from 30 to 14. So the temperature reduction is also there. Okay. The most important thing is we have to note that what is the difference between the sensible cooling and cooling with the dehumidification. So moisture gets separated. So that means what is the meaning? So the cooling coil surface will be at a temperature less than the dew point temperature. If the cooling coil surface is at a temperature less than the dew point temperature, the condensate moisture present at the surface of the coil, it will be trying to separate out. Okay, so it will be trying to separate out. Okay, and the amount of moisture will be that amount of moisture will be collected. So you may be knowing in AC there will be a drain pipe. So in the drain pipe, water will be coming out. So that water is this water only. Okay, so that water is this water only. So how much is the quantity of water it is collected? We can calculate very easily. So this is a W1, that is specific humidity 1. This is specific humidity 2. Find the difference. Omega 1 and omega 2. So specific humidity at 1 and specific humidity at 2. Find the difference. Just multiply by the mass flow rate of air. I'll be getting the amount of moisture collected. So that is the thermodynamically given. Physically, I told this is thermodynamically given here. The dry air mass balance, the mass of air at 1, mass of air at 2. So it is the same. Similarly, water mass balance. Okay, so what is happening to the water? So the mass of water vapor present at inlet will not be equal to water vapor at the outlet, because some amount of moisture is removed because of condensation. Okay, so that means at inlet I will be having higher moisture, because of cooling process amount of moisture is removed. At the exit I will be having lesser moisture. So the balance is like this: at inlet I have more moisture, at the exit this moisture is removed, plus this lower moisture content. Okay, so this is the mass balance. So what is MW? Then it will be higher mass, that higher moisture, that is omega 1 Ma into omega 1 minus omega 2. Okay, so that means the difference in moisture, okay, it is given by this. Okay, you can calculate it. So and what is happening to the energy balance? So whatever the enthalpy at inlet, okay, so M1H1, okay, so you know it will be higher because it is going for a cooling coil. It will be higher, it will be higher here. So as it goes, okay, so it will, the heat is removed, so the exit enthalpy will be lesser. So what is the meaning of that? So this value, this enthalpy value at inlet will be equal to removed plus exit. Okay, so when I try to find out what is Q out, so Q out will be, you put it on one side, so I'll be having M into H1 minus H2, and you have to remove the you are removing latent heat also. So that component also, this is the mass of water vapor removed, that mass of water vapor removed and the corresponding latent heat I have to put it here. Okay, so now I will be getting what is the Q out. Okay, so that is the energy balance. So this is the cooling and dehumidification system what you will be having in the house. This is used for summer air conditioning. Okay, so especially this is suitable for hot and humid conditions. Okay, okay, fine. So next is heating and humidification. So winter air conditioning, psychrometric of winter air conditioning. So that means already I told you, so if it is winter, the temperature will be lower, humidity will be lesser. So this is the starting point. So what is my, if I have to go for room design condition, what I have to do? I have to add heat as well as I have to add the humidity. Now I told you what is RH. RH tells you about the moisture adding potential of the air. Suppose if I am trying to add humidity at this point, you know that the moisture adding potential will be very much lesser. So what I am doing, first I am heating it. So when I am heating it, what happens? The moisture adding potential increases. Already I told you in a term. So moisture added potential, now it is higher. So now what I am doing, then I am spraying. So when I am spraying, then so my moisture level is increasing. So now then I am going to the room design condition. So that is the concept behind the heating and the humidification. Why we are heating? We are increasing the moisture absorbing potential. So and after that we are humidifying. So then it can hold a large quantity of humidity, which is required for winter air conditioning. Because you should know, in winter outside it may be ice or it may be dry. Okay, so inside, okay, so inside there may be humidity because of the. So what will happen? Humidity will be lost to the surrounding. Okay, humidity will be lost to the surrounding. So if you are trying to take the fresh air from the outside, what will happen? The fresh air from outside will be dry. Okay, so that dry air, if you are using it, is not good. So we require a specific humidity, like 50%, 50 to 60% humidity. It is essential. So for that, what we are doing, we are heating as well as we are adding the humidity. So that is what is happening here. Okay, so this is winter air conditioning. This is winter air conditioning, and here you can see the first portion 1 to 2. The energy balance is like this. Air mass balance is maintained. Even this is sensible because even moisture balance is also maintained. So what is the heat added? Heat added, you know, in the heating coil, before you will be having lesser enthalpy. After that you will be having higher enthalpy. After heating you will be having higher enthalpy. Higher enthalpy minus lesser enthalpy into the mass flow rate of air. It is going to be the heat added. Okay, so that is what I am having here. And where I am adding humidity? I am adding humidity after this. Okay, so how much humidity I am adding? So 2 to 3 condition. 2 to 3 condition. So this is 2 is less humidity condition, 3 is higher humidity condition. So higher humidity condition, okay, so this will be equal to lower humidity condition plus humidity added. Okay, so this is MAW2 plus M dot W is equal to M higher humidity condition, M dot A3 into 7. Now I want what is MW. So MW will be higher humidity condition minus lower humidity condition into mass flow rate of air. So from that I can find out what is the mass flow. So this is a simple summer air conditioning and a simple winter air conditioning. Okay, I request the participants. Okay, so I just request the participants to paddle with me. So today we have a little bit more discussion. So I request the participant to stay with me. Okay. And okay, so what is evaporative cooling? Okay, so what is evaporative cooling? Where we can go for evaporative cooling. So here you can see that this is the hot and dry condition. Dry means in this point the humidity will be very much lesser. Specific humidity is lesser, and here dry bulb temperature is very much higher. So this is hot and dry point. So usually in desert conditions we'll be having this. So in the desert conditions, you need not go for cooling and humidification systems. Okay, so there you can go for evaporative cooling because the water present in the desert condition, so it has the potential of cooling the air. Why? Because you can see here the starting point itself, it is at a low relative humidity. So you would have seen the relative humidity lines. It will be lining like this. The starting point here, it is a low relative humidity condition. That means there is more potential for adding the moisture. Okay, so because of that, what we are doing, we are just taking the water and spraying. Okay, like in like a adiabatic humidifier. Okay, so if I am just spraying the water, okay, so I am taking the hot dry air, I am just spraying the liquid water. So what is happening? My temperature is dropping. How long my temperature? How long this temperature will drop? It will drop up to wet bulb temperature. It will drop up to wet bulb temperature. Beyond that, it will not drop. Okay, but this dropping, okay, this wet bulb dropping up to wet bulb temperature, it is possible in dry conditions, hot and dry conditions only. If I do the same thing in Chennai, okay, so that is not possible. Already I am closer to the saturation line. So now if I am going to pour water into my system, then what happens? So there will not be any drop. Okay, so think that if you are already in this place, if you are already in at 2, already at 2, okay, so now if you are trying to do that, okay, if you are trying to do evaporative cooling, what will happen? Only a small drop in temperature is there. But if you are at the hot and dry condition, okay, so there is a large potential. Okay, so that is what we call as adiabatic saturation process or constant wet bulb compress or enthalpy, constant enthalpy process. At the constant enthalpy, we are spraying the water. So because of that, we are getting the drop in temperature. This drop in temperature is possible up to wet bulb temperature. Why I am discussing this? This is free. Okay, this is free. It's a very simple system. You don't require any cooling and all, external cooling and all, mechanical cooling, compression system, vapor compression system like that. It is not required. Okay, so that is why I am discussing here, and it is also very good because it is adding moisture to the surrounding. Okay, so it's very important. Okay, so this is what we call it as evaporative cooling. It is what we call it as evaporative cooling. So this is applicable to hot and dry condition. Okay, and if you want to improve the cooling, you can go for sensible cooling also. So you can have sensible cooling, but spraying of water. Okay, spraying of water, it is very important in evaporative cooling. And whatever the air cooler we are having in our house, it will work in very good in hot and dry condition. Okay, so in hot and dry condition, it will work very good because relative humidity is less, one thing, and wet bulb temperature, difference between the wet bulb and the dry bulb temperature, it is very much higher. That means the wet bulb depression is higher. So because of that, there is more potential of adding moisture. Okay, so this is what we call it as evaporative cooling. Okay, and mixing of air streams, that is also an important thing in air conditioning system. In an air conditioning system, so this is very common. Okay, so if you are not mixing, you think that you are taking the air from outside, and if you are cooling it and you are throwing it inside the room, and after that you are sending it outside. Okay, so that is called 100% fresh air application. So if I do like this, a large amount of energy will be required. Okay, because always outside the air will be very hot, and if you are trying to cool it, okay, the tonnage required will be very much higher. Okay, but instead of that, usually in our household air conditioners, what we will be doing it, we will be taking air from outside and we will be recirculating the air. The amount of air recirculated, it will be very much higher compared to air which is taken from outside. Okay, so this saves the energy for us. Okay, this saves the energy for us. So in that construct, that thermodynamic mixing process or adiabatic mixing process is very important. Okay, so I'm not going to discuss about all these things. So what we have to do is think that there is one condition. Okay, condition 1, and I have another condition, condition 2, and both are mixing. Okay, when both are mixing, what is happening? I'm getting the third condition. So we are interested in noting what is H3 and what is omega 3, specific humidity 3. Okay, So now, what is the concept? How you can understand very easily? Okay. So I have a condition here. I have a condition here. So if you see this formula, okay. So if you see this formula, it is like a weighted average. Okay. So it is like a weighted average or a weighted condition. So you can see this in a center of gravity application. Same like a formula you will see in the center of gravity application. Okay. It means that where is the center of gravity? So wherever the weight is more, the center of gravity will be more in that location. So that is the same formula we are having. Okay, I will put it in another form where you will be understand. So a simple example is think that we are taking a cold air from the room, okay, and we are taking fresh air from outside. Fresh air will be hot, and the cold air from the room, okay, so it will be at a lower temperature, okay. Think that I'm taking a 99 kg of recirculated air, and if I'm taking 1 kg of air from outside, okay, or 99 kg per second of recirculated air, 1 kg per second of fresh air. So if I mix both, what is the resultant condition expected? The resultant enthalpy will be the enthalpy of whatever it is more, that is the enthalpy of the cold air only. So that is what this formula is telling. Okay, so if you put it like this, so it will be like specific humidity 1 mass of air 1 plus specific humidity 2 mass of air 2 divided by I'll be having mass of air 1 plus mass of air 2. Okay, that is specific humidity 3. Similarly, enthalpy, if you want to find out, it is Ma H1 plus Ma2 H2 divided by Ma1 plus Ma2. Okay, so what will be the resultant enthalpy? The resultant enthalpy will be the condition. So it will weigh between these two mass. Okay, whichever the mass which is having more, okay, the condition will be closer to that. So that is what we have to understand. So this is very common. So usually when you are going for air conditioning system design in a site, you will find that you will be recirculation quantity will be very much higher. Fresh air taken will be very much smaller. So when you are trying to mix both, what will be the resultant enthalpy? The resultant enthalpy will be more towards the recirculated air. Whatever the example I told, 99 kg per second of recirculated air, 1 kg per second of fresh air. If I mix both, what will be the resultant condition? So the resultant condition will be the cold air condition, lower enthalpy only. Okay, why it is? Because of this weighted average formula. Similarly, you think like this also. I'm taking a 99 kg of cold recirculated air, which is having less humidity. I'm taking only 1 kg per second of fresh air, which is having higher humidity. Now I am mixing both. What will be the resultant humidity? The resultant humidity will be corresponding to whatever it is having for the cold air or recirculated air. That means lesser humidity only, because you are having 99 kg per second of less humidity air and 1 kg per second of high humidity air. The resultant air will be having a less humidity only. Okay, so this is this formula you have to understand like that only. Okay, so that is fine. So if you go to other textbooks, it will be like this. So other types of formula it is given here. So we will go the next process. Okay. Now, as per yesterday's discussion, so we will find some of the area, all the climatic conditions in the world. You can bring it in the psychrometric chart. Chennai condition will be somewhere here. Then you should not tell only Chennai condition means always it will be here. No, during winter it will come down. Okay, it will be somewhere here only. Okay, it will be somewhere pleasant. So that means in the psychrometric chart, Chennai conditions, it will not be fixed at some position. Okay, during summer it will be here. During winter it will be somewhere here. 25 between 25 and 30 it will be somewhere here. Similarly, even if I am taking England or Scandinavian countries, which is cold and dry, so it will be somewhere here. So it will not be always here. So when it is June, okay, so June solstice, it will move from here to here. So it will go towards cool and moderate climate. Okay, so that means the conditions in the psychrometric chart, okay, it will be changing. If I'm taking a location, if I'm taking Chennai, so depending on the climatic latitude and depending on the time of the year, okay, so depending on the location and depending on the time of the year, the psychrometric conditions will be varying. So we have to take all the extreme conditions for designing. Okay, so you should not take only summer conditions. Sometimes the humidity may be more in some other conditions. So we have to see which are the heavier conditions that we have to take it for the design. Okay. So we are interested in knowing that only. Okay, so now before this, we don't know about the psychrometric chart. Now we know about the psychrometric chart. Psychrometric chart, this is sensible portion, this is latent portion. Okay, this is heating, cooling, moisture addition, moisture removal, so saturation. So all these things, you know, this is hot and humid condition. This is cold and dry condition. This is unbearable cold condition, cold and dry condition. Okay, so this is warm and humid condition. So everything I have to bring it to this moderate condition. So what is this? 25% dry bulb temperature and 50% RH. I think there are a lot of studies about this. It is like a zone. Okay, it's a comfort zone. So we have to bring all the climatic condition towards that comfort zone by mechanical cooling or passive cooling or solar heating or by mechanical heating. Okay, so that is the concept what we are studying. Okay, fine. Okay, summer air conditioning in a dry condition. Okay, so summer air conditioning. So already I told in the psychrometrics are the dry portion will be at high temperature and low humidity. So this is the plan. So what I have to do? I have to do the cooling. Now before this we have seen adiabatic saturation process, that is using an air washer. We can do that. In the dry condition, we can. I told even you can use cooling coil. So you can use cooling coil. You can go for sensible cooling. Okay, and so it should not be below the dew point temperature. If you do the below the dew point temperature, the surrounding humidity will come down. And after that, what I am doing, I am spraying the adiabatic humidifier. I am spraying water. Okay, so because of that, cooling is taking place. Humidification also it is taking place. Adiabatic humidification at constant enthalpy humidification is taking place. So this is the final condition. So this is summer air conditioning for dry condition. So for that is at this point. If you are at this point, you can use air washer, or you can use your household air cooler. Okay, and you can go for a cooling and humidification system also. So that is what we are seeing here. Okay, and if you are going for summer air conditioning, okay, when we are going for summer air conditioning, what is that we have to do? When we are going for summer air conditioning, okay, the actual setup will be like this one. Okay. So this is a comprehensive picture. So whatever we have studied, that is a theoretical. Okay. So in actual reality, the summer air conditioning will be like this only. So here, what is happening? Okay. So this is an air conditioning system. I have the refrigeration system. I have the cooling coil here. I have the fan here. I have the filter here. So this is the return air from the room. Okay, and this is the supply air from the room. So this is the room, which is where all the loads are present. Okay. So I have the glass load. I have the conductive load, I have the infiltration load, room heat gain, everything is there. So one thing is not there. One thing which is not there is fresh air is not there. We are not taking fresh air. Okay, and this is air conditioning systems. It is a typical air conditioning system. You will have filter, fan, cooling coil, which is for a summer air conditioning system. So already I told you. So why we are going? Why we are going for cooling load calculation? We are trying to find out what is the rate of heat entry into the building. So how much, what is the rate of solar energy entry into the building? What is the rate of heat generation inside the building? What is the rate of heat, outdoor air heat, if at all, if it is there, if it is entering into the building. So if it is infiltration, it will be entering into the building. So this rate of heat entering into the building, I have to sum it, okay? And accordingly, I have to select the equipment. This rate of heat entry into the building, heat gain into the building, that should be equal to, at least it should be equal to the rate of cooling by the cooling equipment, okay? Or the rate of the cooling equipment should be much greater than the rate of heating by the system, okay? We are designing it for the maximum rate of heating. So throughout the year, we are finding what is the maximum rate of heating. So that will happen at some point. For example, Chennai, we take April, May, we take a specific point, and at that point we say that the radiation is more and heat received is more. At one point of time only we are doing, at 1 hour, okay, 1 hour where the rate of heat entry into the building is maximum. So we have to take all the combination, everything we have to take it. So and consolidated when it is maximum. So that only we have to take it. Okay. So that then only this system will be capable of cooling this system and maintaining the temperature inside the room. Okay. So this we have discussed yesterday also. Okay. And what are all the important parameters in the design of the summer air conditioning system? In the design of the summer air conditioning system, if you are not taking any heat from the if you are not taking any pressure. Okay, so this will be the simple system. So just now what we have seen, that is the same. We are having a sensible heat addition. Okay, so there is a heat gain inside the building, and we are taking the air and we are cooling and dehumidifying and we are supplying into the room. So now there is a factor called a sensible heat factor. So what is the sensible heat factor? Okay, so I have the room. In the room, whatever the heat is added, okay, sensible heat added, it is called as room sensible heat. If what are all the latent heat which is added inside the room, so that is called room latent heat. And the room sensible heat and the room latent heat put together, it is called as room total heat. Okay, so I have the room, I have the sensible heat added because of the things. So I may have a latent heat also because of the moisture generated by the occupants. So or because of some cooking items are there, cooking systems are there inside, or because of infiltration, some moisture generation will be there. Okay, so that is room latent heat. Similarly, the load inside this room, it is called room sensible heat. If I club both together, so that is called as room total heat. Okay, and we have to mind that we are not taking outdoor air heat at all. Okay, and we are trying to find out what is the sensible heat factor. The sensible heat factor, it is the ratio of sensible heat to ratio of total heat. Ratio of sensible heat means sensible heat by sensible plus latent. Okay, so most of us will be wondering what is the importance of this sensible heat factor. Why we are choosing this sensible heat factor? So sensible heat factor, it decides the room condition. Okay, supply and room condition. Okay, so inside the room, this only will be happening. Supply will be there here. The air will be getting heating. Okay, so the air will be getting heating and humidified. We are doing the cooling and dehumidification. Our external equipment will do the cooling and dehumidification. But if the cold dehumidified air, cold and dehumidified, if it is entering into the building, what will happen? It will come to this point and it will be getting heating and humidified up to room condition. Okay, so that is what will be happening. So that means SR, it is the path at which what will be happening inside the room. Okay, and now this is very, very important. There are some places where the room latent load will be negligible. There are some places where the room latent load will be very much higher, especially in the places like Chennai and the coastal areas. The room latent load will be very much higher. So what happens if the room latent load becomes higher? So that means this vertical axis will be more and compared to the horizontal axis. Horizontal axis, it will be depending on the sensible heat, but this vertical axis, it depends on the room latent load. If there is a thing that if the room latent load is somewhere here, okay, so that means my sensible heat factor will be very much smaller only. Think that the sensible heat latent heat is 0, then means my sensible heat factor line, okay, the slope of the sensible heat factor line will be 0. A small latent heat, okay, a lesser slope will be there. If I keep on adding the sensible heat, I mean latent heat, I'm sorry, if I'm adding keep on adding the latent heat, so I will find that the slope will be increasing. Okay, so like that it will be increasing. Okay, so that means that is the sensible heat factor means your cooling equipment should be capable of meeting this requirement of larger latent load compared to sensible load. Similarly, your cooling equipment should be capable of meeting the requirement of smaller latent load compared to the sensible load. So that is decided by the sensible heat factor line. Okay, so that means how equipment can meet that requirement. That can meet that requirement by maintaining the low ADP. How you can maintain a low ADP, or you can decrease the bypass factor. So that means it is something to do with the design. Okay, so your cooling coil design. So that means the sensible heat factor line, okay, it represents the slope, or it represents the ratio of the sensibility to latent heat, and it tells, okay, it tells how much is the latent heat. In simple words, it just tells that how much is the latent heat. If the latent heat is lesser, okay, the slope will be smaller. If latent heat is more, the slope will be higher, and accordingly we will be making the design. Okay, accordingly we will be making the design. And if this line, if it is like this, it will go to the ADP up to some point, and if this line is somewhere like this, you will find that if this is a starting point, if your line is like this, your ADP will be different. Similarly, if the slope is something different, so that means the room sensible heat factor, it has relevance with the ADP. Okay, it has relevance with the ADP. So that means if you have more humidity inside the room, so you have to go for a very low ADP. So that significance is attached with the sensible heat factor. Okay. Okay. So now I'm taking the room. In the room, this is the inlet condition. I'm not taking fresh air. So this is the ADP. And what about the amount of mass of air required? So our volume of air required. So if I'm having, this is the sensible heat factor line, okay, and this is the inlet condition, this is the ADP condition. Suppose if I'm having, okay, suppose if I'm having the room sensible heat, constant room sensible heat, if my temperature ADP is very much lower, so it is going like RSH is equal to CMM min into this factor into delta, okay. So that means if my ADP is lower, it means that this difference is higher. So if this difference is higher, what will happen to the CMM? Denominator is higher, okay. RSH is constant. So what will happen to CMM minimum? CMM minimum will be very much lesser. Denominator is greater, it will become very much lesser. So what is the meaning? What is that we have to understand? If your supply air point is near the ADP line, so the mass of air circulated or the volume of air circulated, it can be smaller. Now, if your supply point is shifting here, okay, so along this line, anywhere you can supply, along this sensible heat factor line or SR line, anywhere you can have your supply point that will cater the load, okay, except that if you are here, the temperature difference will be higher. If you are here, the temperature difference will be smaller. So if you are moving in this point, so if you are here, so that means what will happen? Amount of the mass of air, air circulated will be more, and if I'm moving here, still it will be more. So it's very simple. If delta T is smaller, mass will be increasing, or the volume of air circulated will be increasing. So that is what we have to understand from this discussion. Okay. So this is a CMM minimum. Okay. So this is CMM minimum, and if you want to calculate CMM, yes. Okay. So you can that is at this point. So same RSH divided by Ti minus Ts. This is Ti minus Ts. Okay. And the same thing, if you are using bypass factor, you can use Ti minus TADP. You multiply by 1 minus bypass factor. Okay. So this product of these two will be equal to this. Okay. Okay. So this is the concept. I just want you to understand the concept. The concept is when you are moving from a lower temperature to a higher temperature or in supply, while supplying the air into the room, if your temperature of supply, if it is higher, the mass of air circulated will be more. This is very simple, you can understand. So if you think whenever you are putting fan, okay, so you will be putting at a high speed and you will be sitting. So that means air circulated is higher, but the temperature difference is smaller. But when you are putting AC, you will not go for a same amount of mass. You will not go for same amount of, because you know the temperature drop in AC is very much higher. So only lesser mass is circulated. I mean, lesser volume flow rate fan is taken. But when you are using your household fan, the temperature difference is smaller. So for feeling comfortable, what you are doing, so the mass flow rate is higher. So that concept only it is applied here. Okay. Okay. So now we have to go for summer air conditioning with outdoor. Okay. So we have a case where summer air conditioning without outdoor. Okay. So without outdoor air. So next, what is the contribution of summer air conditioning with outdoor air? So the contribution of summer air conditioning with outdoor air, we find that we are adding air from outside. So when we are taking air from outside, it will bring the load from outside. So it will bring the load from outside. So when it is bringing the load, it will be having both sensible load as well as latent load. So you have outdoor air sensible load, and you will be having outdoor air latent load. Okay. So both will be adding. Okay. And so what will be happening to the psychrometric? Okay. So now we will go for the psychrometric. So what is happening here? This is the full for this diagram. Okay. So this is the full psychrometric chart or psychrometric processes for this. Okay. What is happening? We are taking the outdoor air. We are taking the room air. Okay. We are mixing it. So we have studied about mixing process. Okay, mixing process in psychrometry. Okay, so that is what will be happening here. So what is that we have learned in the mixing process? The concept is simple. Whatever the mass is more, that condition will be taken. So here we will be mostly in an air conditioning system. The recirculated air will be more. The fresh air taken will be very much smaller. So because of that, the condition will be like uh, the resultant condition of mixing will be like having lower temperature. More will be like room temperature only. Okay. And after mixing, so that is what is happening. You are taking outdoor air. So you think that it is Chennai condition. So it is hot and humid, and this is room condition. So like what I told. So you think that 99 kg per second of room air is taken, 1 kg per second of outer air is taken, and we are mixing it. Okay. So after that, what we are taking, we are sending it to the cooling coil. So when I am sending it through a cooling coil, what is happening? MA is cooling and dehumidification process. That process also we have seen in psychrometry. We have seen the mixing process, then we have seen the cooling and dehumidification process. Okay. And we have to discuss about bypass factor. What is bypass factor? So whenever you are sending air through a coil, whether it is heating coil or cooling coil, all the air will not be getting cooled. Okay. So it is because of the effectiveness of heat exchanger. You may be knowing all the effective heat exchanger will not have a 10% effectiveness. So some amount of air will be bypassed. Okay. So because of ineffectiveness of the heat exchanger. So that bypass, okay, or bypass portion, so that is called as bypass factor. Okay. So what is bypass factor? So bypass factor, it is the measure of inefficiency of the cooling coil. Okay. So some portion of the air, it is not at all converted into required temperature, or it is bypassing the cooling coil. And 1 minus bypass factor, it is like the efficiency of the cooling coil. That much amount only it is capable of converting from the to the prescribed condition, to the cooled condition. Okay. So that means if I am cooling it from M to A, so the cooling will happen only up to S condition. Okay. And RA, what is RA? This is room condition, and this is a ADP condition. Okay. So a typical thing is happening here. So you are finding that the mixing condition, it is meeting the ADP condition, and the next one is I'm finding the room condition. Also, it is going and meeting the condition, ADP condition. But you are seeing that the air from the cooling coil, okay, it is not crossing the room sensible heat factor line. Room sensible heat, if you want to meet the requirement, the air, okay, the supply point should be somewhere in the room sensible heat factor line. So that means it should be in the SR line. Okay, it should be in the SR line. So now you are finding that your SR line is with the ADP, and your mixing condition MA also, it is going and directly meeting the ADP. So that means you will not have the supply condition, or you will have the supply condition at the ADP. So that which is not possible, because some amount of air will be bypassed. No, so that means it is not possible. So what is the solution to this problem? So what you can do is, instead of going to this ADP, still you go for a very low ADP. So that means you make the mixing condition, okay, to cross this line, to cross this sensible heat factor line, or SR line. So when it is crossing, so the resultant place, okay, so for example, so you take this is like this. So this is SR line. Okay, this is SR line. This is mixing condition line, which is from the cooling coil. So this is entry into the cooling coil. This is exit of the cooling coil. So now what is happening? So both are intersecting at this point. So now what is happening? The condition of the air from the cooling coil, okay, at this point it is capable of supplying to the room. Okay. So SR is the room condition. So this is the supply point. Okay. So how you did that? So by reducing the ADP. So I'm not choosing the ADP as per SR line. Okay. So I'm reducing the ADP. Okay. Such that my bypass factor. Okay. So the bypass is coming here, and 1 minus bypass is coming in this place. Okay. Okay. So now we are ready. Okay. Now we are ready. Okay. So this is a summer air conditioning system. So I'm taking outdoor air and I'm mixing it with the indoor air. So why I'm mixing with the indoor air? Because if I am not mixing with the indoor air, just if I am taking the outdoor air, my total cooling will be from this point, outdoor air, to up to this ADP. So now since I am mixing, in reality, this will be very close to this one. So if you are calculating, this will be very close. So this is exaggerated. Okay. So the mixing condition will be somewhere here. So now what is the tonnage? Okay, so what will be the cooling capacity? Now the cooling capacity is reduced. So this is constant enthalpy line here, and this is the constant enthalpy line here. Okay, so just 1 minute, I will go there so that you can understand better. Just pattern with me today. Just pattern with me. Some timing limitation is there. We will complete with this discussion. Okay, we'll complete with this discussion. So now if I am starting from this point, okay, so I'm sorry. Okay, so if I am starting from this point and ending at this point, okay, that means 100% pressure. I'm taking 100% pressure. So you know, from this, okay, so from this point and from this point, so the cooling coil capacity will be very much higher. So now what is happening, since I am mixing the air, room air with this, so what is happening is just okay, so this is the condition. So now the cooling coil capacity is from M to, okay, and now it is intersecting at this point. Okay, so now it is intersecting at this point. So since it is so now my supply point is like this much. Okay, so the process, it is mixing process from here to here. Okay, so it has to go up to ADP. Because of the bypass, now the supply condition will be this one, from S to R. Okay, so that is the room condition. Okay, what is happening into the room? What will happen into the room? The load because of the load. Okay, so there will be what is this process? Heating and humidification. So try to understand. So cooling coil, it will try to cooling and dehumidify. Okay, but inside the room, because of the load, what will happen? So that means inside the room, because of the load, what will happen? Heating and humidification only will be taking place, because to the enclosure, heat is sensible, it is added, latent heat is added. Okay, even outdoor air heat, everything it is added. So because of that, and inside we will be adding moisture. Inside we will be adding the load, system load also. So because of that, what will happen? Because of our load, this only will be happening. So that means the room air will be heating and humidified. So where cooling is happening? So in the cooling coil, so we are cooling and dehumidifying. So that is how we are having a perfect air conditioning process. Okay, so I am explaining all these things because when we go for a cooling load calculation, so this topics will come. Okay, so these topics will come. So that is why I am discussing that. Okay, how you are calculating the cooling load? Okay, so now in a summer air conditioning system, how we are calculating the cooling load? Okay, it is very simple. So if I am taking the room sensible heat factor line, so inside in the room you will be having sensible and latent heat. Okay, so similarly from the outdoor air, okay, whatever you are taking, so you will be having sensible and latent heat. Okay, similarly the bypass. Okay, so because of the bypass, you will be load will be there because of the bypass. So it will be having a sensible and a latent heat. Okay, so you know, if this is SR, the horizontal to drawn to that will be sensible load, and vertical to that it latent load. Similarly, if this is the outdoor, okay, so because of mixing, I am getting the load. This is latent load and this is a sensible load. Similarly, this bypass, because of bypass, I will be having latent and sensible. So all these things put together, it will be constituting the load for the cooling coil. Okay, so that is how I have the room condition. So I have the room sensible heat, I have the room latent heat and room total heat and the room sensible heat factor. Okay, now how to calculate the total tonnage? Okay, so how to calculate the total tonnage? So for that, you calculate the room sensible heat, room latent heat, room total heat, and you can calculate outdoor air total heat and outdoor air sensible heat also. Okay, what is outdoor air total heat? This MCP delta. What is M? Density into volume into the enthalpy difference. Okay, so that I have it a kilowatt. You always understand it is in watts. It is the rate of heating. Okay, rate of heating. Please try to understand. Similarly, since latent heat. Okay, so I think this is total heat. So I will be having sensible heat also. Okay, so sensible heat is MCP delta. Okay, so this is volume into density mass. Okay, CP into difference. Okay, outside and room temperature difference. Okay, So this is outdoor air sensibility. Similarly, you can calculate what is outdoor air latent heat also. Okay. So I think it is not shown here. Okay. So how to calculate the grand total heat? The grand total heat is room sensible heat plus outdoor air sensible heat plus the air conditioning system gains. Okay. Similarly, room latent heat. It is room latent heat, outdoor air latent heat plus system air gains. Okay, because of latent heat. Now just you add these two. Okay, I'll be getting grand total heat. So when you go to the psychrometric chart, so you will be finding 1 minus bypass factor, everything. All these things will be there. So those things and all, it will be confusing you. Okay, it's very simple only. So what is the room grand total heat? It is total sensible heat plus total latent heat. What is the total latent heat? It is room latent heat, outdoor latent heat, and the system gain because of latent heat. And similarly, next, what is the room sensible heat? It is room sensible heat, outdoor air sensible heat, and the air system gains. Okay, you may be wondering when you are calculating, there was 1 minus bypass factor would be there, and another place just bypass factor will be there. So that is how, if you add 1 minus bypass factor and the bypass factor put together, it will become 1. That is how your outdoor air sensible heat, it can be taken as 1 itself. Similarly, here also, you'll be having 1 minus bypass factor into outdoor air latent heat and bypass factor into outdoor air latent heat. Instead of doing that, you can just take it as outdoor air latent heat. Okay. Okay. Now that we have calculated the total heat. Okay, we have calculated the total heat. So that is the rate of heat entry into the building. Okay, rate of heat entry into the building at a particular point. Okay, so at a particular point. Okay, so at a particular timing. So that is what we are doing. Okay. So if you are calculating the rate of heat entry every hour throughout the day, so that means you can know what is the pattern of load inside the conditioned space. What is the pattern of load inside the conditioned space? That you can do it. Okay. So that information will be very useful for us for doing the energy calculation. So when I come to energy calculation, I will explain you in the detail. Okay. And the last, we have to decide what will be the dehumidified CFM, or what will be the AHU volume flow rate. Okay, so that is very important. So for that, we will be having an effective room sensible heat. Okay, so what is effective room sensible heat? So this is a effective room sensible heat line. Okay, so this is a effective room sensible heat. This is room sensible heat line. This is bypass factor into the cooling coil component. Okay, so that is there. So what is the effective room sensible heat line? So I have room sensible heat and bypass factor into outdoor air sensible heat, then air sensible heat, air conditioning gains. Okay. Similarly, effective room latent heat. I have room latent heat, bypass factor into outdoor air latent heat, and the air conditioning system. So when I put both together, I'll be having effective room total heat. But better than this is very useful. Effective room sensible heat factor. This is useful because for finding the dehumidified air supply. So effective room sensible heat factor, it is just like sensible heat factor only. It is effective room sensible heat divided by effective room total heat. Okay. So from the effective room sensible heat, it is which is in kilowatt. How you are finding the dehumidified air quantity? By using MCP del T only. Okay. So what is M density into volume? So it has gone to the other side. So just equal ERSH is equal to MCP del T. What is M? Density into volume. So that the dehumidified air volume, it has gone to the other side. CP is this value. It is to a room dry bulb temperature minus ADP. Okay, dry bulb temperature minus ADP. Okay, so using this relation only, we are finding the dehumidified volume. So this dehumidified supply volume, it is useful for deciding the AHU capacity, volume flow rate of AHU. Okay, so this is about the summer air conditioning system. Okay, so this is about a summer air conditioning system. So whenever I am discussing about some topic, I discuss some part of topic which I am going to discuss subsequently. So that means here in summer air conditioning system, I have discussed about some topics which will be useful for heating and cooling load calculation. So here also I have discussed about the topics connected with the load calculation. Okay, so that is effective room sensible heat, grand total heat, dehumidified air CFM. So all these things I have discussed. So these things we are going to discuss in detail tomorrow. So what are all the components of that we have to understand. So that I have discussed now. Okay, and the same thing we can extend it to the winter air conditioning. I think all of you might be knowing this winter air conditioning. So I'm taking, if it is a winter air conditioning, I'm going to take the air from outside. So I'm going to heat it, and then I'm going to humidify it, and then again I'm going to heat it. What is the purpose of this heating coil? It will increase the RH. I mean, I'm sorry, it will decrease the RH. It will increase the temperature. It will decrease the RH, so that you can add more amount of moisture. And after that, again you are reheating, okay, to supply into the room. So the process will be like this. So if you are in the process, first you are going to preheat, then you are spraying in the adiabatic saturation, then you are going to reheat. Then what you are doing? So you are going to the, from the cold condition, you are going to the hot condition. Okay, so from cold condition, we are going to the room condition. That is the better way to tell. From the cold condition, I am first preheating it. Okay, for increasing the decreasing the RH, so that more moisture can be added. Then after that, I am adding the moisture. After that, it is going to saturation. But I don't want to go have a higher RH, so I am reheating that, so that RH can be attained, which can be used, which will be which is comfortable inside the room. Okay, and if it is winter air conditioning, okay, if I am taking outside air also, how the discussion is going to be? Just like now what we had a discussion now, that is going to be like that only. So I have the outdoor air, I have the indoor air. So I am mixing these two. Okay, mixing process we have studied in the psychrometry. So because of that, I am getting this resultant condition. So from here starts our thing: preheating, adiabatic saturation, moisture addition, then again reheating. Okay, so now my supply point is this one. Okay, so this is the room condition, this is the supply point. So this is SR line. So that is the room sensible heat factor line. So previous case in summer air conditioning, what was happening inside the room? The air was getting heated and humidified. Please find what is happening here. The air is getting cooling and dehumidified. So exactly opposite is happening. So in winter place, if you are supplying air inside, what will happen? It will be getting cold. Okay, and after that, what is happening? It will be getting dehumidified. It will be getting dehumidified because it will be dry inside. Okay, it will be getting dehumidified. So here you can see cooling, and the air is getting cooling and dehumidified inside the room. But in summer air conditioning, it will be heating and humidified. Okay, so those things are very interesting to note. Okay, so I think if you are going for cooling load calculation for heating design, so you will be hitting all the sensible heat. Okay, even outdoor air sensible heat also there. Plus you will be adding, you have to know what is the amount of moisture which has to be added, because you have to decide what will be the amount of moisture that can be added, so that for winter design, okay, the room will be comfortable. So that calculation also you have to do it. Okay, I think I have taken a very long time. Okay, sorry for that, but I think all these discussions are important for us. So that's why I've taken a very long time. I beg your pardon. Okay, thank you for things. So now, if at all any question is there, we can have a discussion. Okay, thank you. So you can put your questions in the chat box. So I'm here to answer. Okay. So any question is there? So first of all of you, are you listening?
Yes, sir.
Yeah. So if you have, because I have a lot of today I've discussed so many important things which are very important for energy simulation. So because the quantum to be covered, which is more, I've taken some extra time. Please pardon me. Yesterday, one of the member has mentioned, but still I have done that. I beg your pardon. Okay. So okay. So now just tell me any doubt is there? Okay, regarding the today's discussion. So we can have a discussion. Okay. Can we use trans software for this calculation? See, you can do any other. See, there is something called a hourly analysis program. I think you can do it in Design Builder. So a lot of programs are there. Even each and every company, they are having their own codes. Okay, so that means you can create your own code. So if you ask me, I have my own code for this load calculation. Okay, so I have created. It will be much better than what you are doing in the hand calculation. Okay, so I have created my own code. Okay, so that can simulate everything. Okay, So you can do it. Okay, so you can we can use any type of software. It depends on the accuracy. Okay, so what is the accuracy which you want? So if you are more accurate, you can decide the components very precisely. So that will be very useful for that will be energy saving, and it will be very good for the building. Okay. When we will have the simulation class, sir? Okay, so I will discuss everything about the simulation. Okay, I can show some simulation. Okay, I can show some simulation, but I cannot directly teach you about the simulation, because I think you should understand. Okay, some components are involved, so I cannot give training. Okay, but I can give you the material. Okay, so what are all the materials you have to use it for studying the simulation? Okay, what are all the materials you can use it for studying the simulation? So that I can give you. Okay, so that I can give you, I can help you. Definitely I can help you to learn things. I cannot do it in an online platform. I cannot give training in an online platform. Please try to understand. Okay. Okay, any other question is there? How to know about the descent time of the month for air conditioning? Okay, so the hottest month. Okay, hottest month, and where the latent, sometimes latent load will be very much higher. Okay, for example, in Chennai, the sensible and latent both will be higher. Okay, so there you have to take it. If you go to Bangalore and other conditions, okay, so sometimes the sensible portion will be higher. Sometimes during rainy season, okay, rainy season, the latent load may be higher. So you have to compare it both, which is whatever is maximum, that you have to take it. If latent load is more, okay, and if you are designing based on summer condition, okay, I'm sorry, if you are if you are deciding based on the hottest day, so it is possible that during a heavy latent load condition, so your air conditioner will underperform. It will not give the condition. So that is possible. Okay, so that you have to do a few calculations, and you have to see which will be the maximum. So the rule of thumb is the solar location. Okay, the solar location, you know, at one point of time, the sun will be overhead. So you know, the sun will be going from Tropic of Cancer to Tropic of Capricorn. So it will be in a year it will be going twice. So whenever the sun is overhead about your place, over your latitude, so that is we call it as declination. Okay, so if the declination coincides with your latitude, so that means the sun is overhead. So at that point the radiation will be maximum. So at that point you can do the calculation. Okay, so that is a rule of thumb. But it is possible that by some other loads also the load can become maximum, and it is also possible that your building may not be exposed to outside at all. Okay, so you think there is a multi-storied building, and you know, in the second floor, okay, interior there may be some room will be there. For that, when you are doing the load calculation, there will not be any solar load at all. Okay, so that means there is no question of peak day and other things. Peak day, everything, latent heat, everything, it is there for exposed to conditions, peak solar conditions. Okay, so that means mostly it is common sense. Okay, so you have to common sense will make important thing. Okay, or you can do it for 3 or 4 calculations. Whenever you have high latent load, whenever you have a high sensible load or solar load, you can compare it and then you can do it. Okay, yeah, definitely I'll share the materials to learn the simulation, that I can do it. Okay, will evaporation take place in summer without reaching the boiling point? Will evaporation take place in summer without reaching boiling point of what? Boiling point of what is the boiling?
The boiling point of water.
Boiling point of water.
Water.
Yeah, so see, we can call it as a phase change. Okay, so boiling means usually we call it at 100 degrees and beyond. Okay, so that we call it. So we can call it as phase change. Okay, so you mean at this phase change? Okay, so this phase change will be taking place. Okay, whenever the dew point is reached. Okay, in atmosphere. Okay, when dew point is reached. Okay, so for example, when you are bringing down the temperature, okay, when the atmosphere temperature is going down, so what will happen? The water vapor present in the atmosphere, it will try to stick on the surfaces where the temperature will be low. So for example, car and other things, where metal is there, the temperature will be dropping. So on that surface, okay, it is very common in Chennai. Okay, so on that surface, the droplets will be condensing. So from vapor state, it will go to the liquid state. Okay, and after that, the sun comes. Okay, when the sun is coming, it will evaporate. Okay, so it will heat this water. So it will try to evaporate. When sun is coming, what is the most important thing we have to notice? It will try to heat. When you are heating the air, so your RH will go down. The capacity to hold the moisture, it will be moving up. So because of that, whatever the water vapor it is there, so it will try to evaporate and it will mix with the air. Okay, so you will find that means night time you will find that your moisture. Okay, so your relative humidity will go down. Okay, so your relative humidity of the air will go down. Daytime, your relative humidity is increasing. Okay, basically because all this water vapor it is evaporating. The water from the ocean or water wherever it is present there, it will try to evaporate as the sun temperature increases. Okay, so as seen in the psychrometry, the RH, the capacity to hold the water, it will be increasing. So because of that, more water will be added. So that is why we are having a high humidity or a high relative humidity in our places like Chennai. Okay, but in what will happen in a dry place? So there will not be any water body. So though there is more potential for adding moisture, okay, but water body is not there. So it will retain up to 40% or 50% or 60%. It will retain. But in Chennai, there is water body. So the sea breeze is there. From the sea, air will be coming. So it will be moist. And when the temperature increases, so moisture can be added to the atmospheric air. So that is what will be happening. Okay. So the horizontal line in the cyclone joining the state air represents horizontal line in the cyclone joining the change of state of air represents horizontal line in cyclone joining the change of state of air represents. It is a horizontal line. It is specific humidity line, constant specific humidity line. Okay, so when you are going for sensible cooling and sensible heating, that path will be taking. Okay, at the left hand you will be having the dew point temperature. Okay, I think I have explained more about that. Whatever you are asking. Okay, or I don't know what is that you are expecting. Okay, and next is there is a possibility of dehumidification process without using cooling coil? Yeah, it is possible. The chemical dehumidification and all, it is possible. Okay, so you can have some adsorbent. Okay, it can be liquid or it can be some solid. You know, charcoal and all, it will be absorbing the moisture. So if you are having charcoal, it will absorb moisture and it will make the room dehumidified. So that is possible. Okay, so I will share the presentation. Okay, I will share the presentation in the WhatsApp group. Okay, any other question is there? Whenever you are asking some question, be very clear. Okay, so the horizontal line in psychrometric chart joining the change of state is air represents. So I think I don't know what is that you are expecting. So horizontal line represents a line of constant specific humidity. Okay, when you go in the right direction with increase in temperature, it will keep on increasing, and the left direction, and then it will go and meet the saturation at dew point temperature. Okay, Mr. Yatik Shah. Okay. Yeah, I will share it. Okay, I will share it. Okay. Okay. So I think there is no more questions. There are no more questions. Okay. Yeah. So can you explain about transmission heat gain? Tomorrow we are going to do this, Mr. Kuldeep Parmar. So tomorrow we are going to have a detailed discussion on transmission heat gain. So you will not worry. Okay. Yeah. So we will have a discussion tomorrow because I have not discussed yesterday also. Yeah. Thank you, Christina. Okay. So if there is no more question, thank you everyone. And we will you can post your questions in the WhatsApp, so I can answer you. So no problem. So don't worry, because psychrometric is a very big topic. There will be a lot of doubts will be there. I think you post your question, definitely I will answer, but it may take some time. Okay, so because of my some busy schedule. Okay, so may take some time. Just kindly pardon with me, but definitely I will answer. Okay, yeah. If I am not answering, you repost your question. Okay. Thank you everyone. Okay. So, and I'm sorry that I've taken a very long time today. Okay. Thank you.